Hello, in this video we're going to look at the Nobel Prize in Chemistry for the year 1908, awarded to Ernest Rutherford for his investigation into the disintegration of the elements and the chemistry of radioactive substances. First his work. The discovery of radioactivity in 1896 led to a series of more in-depth investigations. In 1899, Ernest Rutherford demonstrated that there were at least two distinctive types of radiation, alpha radiation and beta radiation. He discovered that radioactive preparations gave rise to the formation of gases. Working with Frederick Soddy, Rutherford advanced the hypothesis that helium gases could be formed from radioactive substances. In the year 1902, he formulated a revolutionary theory that elements could disintegrate and be transformed into other elements. As you can see, this is coming from the official Nobel Prize site. Here you see one of 15 illustrations in the article by Rutherford on the uranium experiment, one of his many articles. This one is coming from Wikipedia, and the next one too, and the others are coming directly from the article. You can see that by looking at the link. Some biographical information summarized by me, coming from the Nobel Prize site. Rutherford's first researches in New Zealand were concerned with the magnetic properties of iron exposed to high-frequency oscillations. He is one of the first to design highly original experiments with high-frequency alternating currents, a time apparatus capable of measuring time intervals of 100,000ths of a second. On his arrival in Cambridge, he invented the detector for electromagnetic waves. He worked jointly with Thomson on the behavior of the ions observed in gases which had been treated with X-rays, Röntgen rays, and also in 1897 on the mobility of ions in relation to the strength of the electric field and on related topics such as the photoelectric effect. In 1898, he reported the existence of alpha and beta rays in uranium radiation and indicated some of their properties. In Montreal, he worked on radioactive bodies, particularly on the emission of alpha rays. With R.B. Owens, he studied the emanation of thorium and discovered a new noble gas, an isotope of radon, which was later to be known as thoron. Frederick Soddy collaborated with Rutherford in creating the disintegration theory of radioactivity with regards radioactive phenomena as atomic and not molecular processes. Soddy also was later rewarded a Nobel Prize, by the way. The theory was supported by a large number of experimental evidence. A number of new radioactive substances were discovered and their position in the series of transformation was fixed. At Manchester, Rutherford continued his research on radium emanation of the alpha rays and in conjunction with H. Geiger, a method of detecting a single alpha particle and counting the numbers emitted from radium was devised. In 1910, his investigations into the scattering of alpha rays and the nature of the inner structure of the atom which caused such scattering led to the postulation of his concept of the nucleus. His greatest contribution to physics. This is the nucleus of the atom, of course. According to him, practically the whole mass of the atom and at the same time all positive charge of the atom is concentrated in a minute space at the center. In 1912, Niels Bohr adapted Rutherford's nuclear structure to Max Planck's quantum theory and so obtained a theory of atomic structure which later improvements, mainly as a result of Heisenberg's concepts, remains valid to this day. In 1913, together with H.G. Moseley, he used, that's Rutherford, cathode rays to bombard atoms of various elements and showed that the inner structure corresponds with a group of lines which characterize the elements. Each element could be assigned an atomic number, and the properties of each element could be defined by this number. In 1919, he discovered that the nuclei of certain light elements, such as nitrogen, could be disintegrated by the impact of energetic alpha particles coming from radioactive sources, and that during this process fast protons were emitted. Well, this was some biographical information summarized by me. If you want to read the complete information, type over this link and you will be able to. Again, an illustration coming from his paper. If you want to study it, pause the video or follow the link. These are coming from the original paper. You see this is an other link than this one. But all the 15 illustrations are coming from this paper. If you want to study in more detail, you best probably follow the link and do so. Yeah? Or pause the video. Then award ceremony speech by Professor K.B. Hasselberg. Early work on the subject by J.J. Thomson, Becquerel and the Curies, all Nobel Prize winners by the way, was done on the subject. Shortly after Becquerel's discovery of these rays are not emitted solely by uranium, Rutherford chose as a subject of investigations involving exceedingly exact methods for measuring their intensity, proving the existence of absolute distinct types of rays, the so-called alpha and beta rays, and establishing more important characteristics of the two types and bringing forward unimpeachable proof of their material nature. Investigation of the radiating phenomena that characterize the element thorium led Rutherford to make the remarkable discovery that element emanates a gaseous substance. Thorium emanation of an elemental nature and with the agency of liquid air has proved capable of being condensed into fluid form. It became clear that the emanation does not arise directly from thorium, but from the so-called thorium X, an intermediate product that may be separated off from thorium and which is continuously formed from it. In itself is due course continually disintegrated, while the gaseous emanation is produced at the same time. The emanation itself, however, is not permanent either. For a short time, it is transmuted into other radioactive substances, which, if the emanation comes in contact with solid bodies, become deposited on them in the form of an exceedingly delicate integument or a so-called active precipitation. The same conditions exist with all the radioactive elements, and it has been possible to prove, especially with respect to radium and actinium, the formation of gaseous emanation in just the same way as with thorium. As these changes accompany the phenomenon of radiance are indeed of an entirely different order of dimension than those occurring during the ordinary chemical reactions and cannot be shown by the balance or even the spectroscope, they can be traced and measured by the far more sensitive electroscope. As will be seen, Rutherford's discovery led to a highly surprising conclusion that the chemical element, in conflict with every theory heretofore advanced, is capable of being transformed into other elements, bringing us back once more to the transmutation theory propounded and upheld by the alchemists of old, but of course in a completely new way. As an explanation of these remarkable phenomena, Rutherford, in conjunction with Dr. F. Soddy, brought forward in 1902 the so-called disintegration theory, which is closely allied with several aspects to the opinions earlier enunciated by J.J. Thomson and other physicists with regard to the nature of matter. According to this theory, the origin and the loss of radioactivity are to be regarded as due to changes not in the molecule but in the atom itself. Radioactive elements are consequently subject to electrical disintegration in such a way that in the space of every unit of time a definite percentage of their atoms are broken up into one or more particles of radiation on the one hand and a new atom on the other, but consequently represents a new element that is different from the original one, owing to the difference it manifests in both its physical and its chemical properties. That new element in its turn be disintegrated into similar matter and so on step by step until finally an atom is evolved, possessed of more stability and permanence. For it must be remembered that the transmutation of the radioactive elements always take place gradually and give rise to the production of a quantity of more or less unstable transitional forms, so-called metaboles. In radium, for instance, as many as 7 at least have been thought to be observable. These ephemeral elements are characterized in the first place by the different rate with which they are transmuted, or, as is often expressed, by the variations in their average length of existence, a constant which is of the same importance in determining the identity of a radioactive element as its atomic weight is for an ordinary stable element. The measurements carried out show that the average length of existence may vary from a few seconds to thousands of millions of years. The disintegration theory was strikingly confirmed by Sir William Ramsay and Dr. Soddy, successfully showing in a most convincing manner how helium originated from radium. This discovery cannot be considered any less interesting or momentous than the circumstance that Rutherford and Soddy had previously expressed the supposition that helium was probably to be regarded as a product of the disintegration of the radioactive elements. Helium is an alpha particle. Finally, the disintegration theory brought to the knot the theory accepted of the stability of the elements among the chemists and met with approval and general recognition remarkably quickly, a fact probably to be ascribed principally to the perspicuity and systematic orderliness that it introduces into the department of radiology. The above-mentioned disintegration theory and the experimental results upon which it is based are synonymous with a new departure in chemistry, involving a fresh and decided extended comprehension of the very basis of that science. To the chemists of the 19th century, the atom and the element represented each in its sphere the uttermost limit of chemical subdivision or disintegration, and at the same time the point beyond which it was impossible for experimental investigation to proceed. This line of demarcation, for so long regarded as unsurmountable, has now been swept away at all events in principle. The results already arrived at are not only of the utmost importance in themselves, but derive perhaps a still greater significance from the numerous possibilities wholly unsuspected 10 or 12 years ago, which have been thrown open from the continuance of the work of investigations in this department of science. As said, this is a summary of the ceremony speech. If you want to read the complete ceremony speech, then you must type over this link. As at the end, still more illustrations from the article I spoke about from 1899 by Rutherford. If you want to study them further, pause the video or follow this link. Yeah, these are the final 4. Okay, this is it for the moment. Next week we will go into the same Nobel Prize, but then the Nobel Prize lecture given by Mr. Rutherford when he accepted the prize. For now, thank you for watching and maybe see you again sometime.